Good evening all, welcome to April's planetary meeting online. Hope you're all keeping well. Thanks to my helpers tonight for preparing and delivering talks, to Gareth, Richard, Julian and Lee. To ensure that we can continue to deliver planetary meetings online, we really need members to get in touch and send us some short videos of what they've been up to in astronomy, whether it's observing, just talking about what you've observed, or a video of your kit, or anything which can be filmed on a smartphone, on a webcam, or as a digital camera. We really do need people to submit things. So get in touch. We can do a bit of editing of the video this end, and then we'll be sure to have meetings going forwards. Tonight's meeting is all about the planet Venus. I'm going to talk first about its place in the solar system. Then Gareth is going to talk about observing and imaging Venus. And then Richard is talking about the transits of Venus. And finally, Julian about missions to Venus, past, present, and future. And then hopefully at the end we'll have time for questions and maybe some answers. If you want to submit your questions through the YouTube live chat, we can collate those during the talk and then hopefully answer them at the end. So, Venus. This is a lovely image of Venus, not taken by me, but by Chris Dole, who's a member of the BAA from Newbury. And this is in the ultraviolet spectrum, taken a few weeks ago. And you can see some lovely detail there, nice sharp edge of the planet and some cloud features. So Venus is often described as the sister of planet Earth, and looking at the two planets side by side here, you can see they're pretty similar in size. Now, all images in my talk are either copyright free or I've got permission to use them. And in the lower right of the screen, you'll see the source of any images. So despite the fact that Venus is similar in size to Earth, it clearly looks very different. So the geology is quite similar. It's got an iron-rich core, it's got a mantle and a solid crust. And on the surface of the planet, there are mountains and valleys and lots of volcanoes on Venus. It doesn't have any moons, unlike us, and there are no rings, unlike other planets. And the atmosphere is very different to Earth. Predominantly carbon dioxide, there's a bit of nitrogen, and there's no minimal magnetic field. And that's probably related to both the geology and its spin. So on this next slide, Lee's kindly put together this graphic for me. And this is looking down from above on the sun in the middle, with the three inner planets in orbit, Mercury, Venus and Earth. It's vanished at the moment, but we'll put it back on. And you can see the closer the planets are to the sun, the quicker they orbit. And all the planets in our solar system orbit in an anti-clockwise fashion around the sun when viewed from above. So Venus is similar in that regard, but Venus is very different in one other aspect, and that's the way it spins on its own axis. Again, viewed from above, all the planets spin in an anti-clockwise fashion. And this graphic here, put together by someone who used to work for NASA, James O'Donoghue, this shows the direction and rate of spin of the planets in our solar system. And you can see the Earth spinning once on its axis in 23 hours, 56 minutes, Mars is pretty similar. Jupiter here, quite fast. Saturn, flat fast. Neptune a bit faster than Earth. Uranus here is on its side. It's probably been knocked 90 degrees off its axis, off its north-south axis. And Mercury very slowly rotates, again in the same direction. It takes 56 days for Mercury, 56 Earth days for Mercury to rotate once on its axis. But Venus is going the other way. It's going in a clockwise direction, and it takes a very long time, 243 days to turn once. And you can just see very slowly this graphic. You can see it turning in the opposite direction, and then the graphic replays and it switches back to the start. So it looks a bit jerky. So this rotation, the wrong way around its axis, is pretty unique to Venus. And there are various theories about this. One theory is that it's been knocked 180 degrees off its axis, so it would have rotated in the plane of the solar system in an anti-clockwise fashion. But being knocked 180 degrees, it's now rotating the wrong way. And here you can see again another graphic just showing the speed isn't correct, but the direction is. Obviously the Earth's rotating anti-clockwise and Venus is rotating clockwise. So Venus completes an orbit of the Sun once in 225 Earth days. So that's comparable with, Mercury does it in 88 days. We do it in 365 days. So Venus sits between the two, so that makes sense. And it takes, as we've just seen, 243 days for it to rotate once on its own axis. So that's a sidereal day. But a solar day on Venus, so sunrise, sunset, back to sunrise, is 117 days on Venus. And because of the reverse rotation around its axis, the sun, if you were standing on the surface of Venus, you would see the sun rise in the west and set in the east. But it would be very slow, long days and long nights. So here we've got another animation. So this is Earth in the foreground, the sun in the middle, and this is the course of Venus rotating around, orbiting around the sun in the course of one of its years. And as you can see, as viewed from Earth, the planet Venus is illuminated in different ways depending on where it is in relation to the sun and to Earth. So you can see when it's opposite the sun, or behind the sun compared to Earth, it's fully illuminated. And when it's between Earth and the sun, it's minimally illuminated. And we can see that here in this other graphic. So again, you can see the orbit of Venus around the sun is in an anti-clockwise fashion. And just as the moon, our own moon, has phases of illumination, Venus and Mercury, because they're inner planets and closer to the sun than us, they also have phases of illumination. When the face of the planet is fully illuminated, it's the other side of the sun to us, and we would call that full. And then gibbous is more than half, and then as it comes round, we've got half phase, and then as it gets nearer to the Earth, we get a crescent, and then when it's new, it becomes a very thin crescent, or when it's very new, brand new, it won't be illuminated at all. And then it goes back around through those phases again, but the other way, so crescent, half, gibbous, and then back to full. Now, there's terms related to this. So when Venus is closest to the Earth, it's a phase called perigee, and when it's furthest away, apogee. So apo, far, G, Earth, peri, near, G, Earth. But also these positions have other terms for them. And for the inner planets, Mercury and Venus, there are these inferior and superior conjunctions. So this is when viewed from Earth, two other objects are in a line. So here we have the Sun and Venus in a line, direct line of sight from us, and that's called the superior conjunction. And then here we have Venus and the Sun in the direct line of sight, and this is the inferior conjunction. So I'll just go back a slide. Now, the astute will notice that the apparent size of Venus in this graphic changes. So when it's near, it's large, and when it's far, it's small. And that's as we would expect. If you see a person in the street and they're near, they look bigger than if they were a long way down the street. And that's the same for everything really in the night sky. Doesn't mean the actual object is changing size, it's just appearing to change size. And we talk about the angular size or angular diameter of objects. Now, the Sun and the Moon are very different in size. The Sun is vast and the Moon is much smaller than the Earth. But in the sky, their angular size is very similar. They're both about half a degree across. And these are two of my pictures which I've tried to show the Moon above and the Sun below at about the same size. Now, the Moon varies its distance from Earth. At times it's far away, and at other times it's closer to the Earth. So again, perigee and apogee. The Moon appears to change size in the sky. And what I've done here is this blue circle represents the Moon when it's furthest away, so at apogee, and then the other Moon, the real photo of the Moon, is resized to show how big it is at perigee. And the difference here is about 15% at maximum. Now below the Sun, because the Earth's orbit isn't fully circular, fully round, it's an ellipse, the Earth distance to the Sun does vary slightly. So the Sun also does appear to change in size in the sky, but this change is less marked than the Moon, and the change is about 3%. Now what I've done is to resize all the planets to show how they vary in size depending on the proximity of the Earth to the planets. And you can see left to right, we've got Mercury, so obviously furthest away and closest. Venus, furthest away and closest. Mars, furthest away, very small and closest. Jupiter and Saturn, and then these small dots here are Uranus and Neptune. And I tried to put Gareth's Pluto on, but it was just too small. So you can see these are all in proportion to the Moon and the Sun. The difference in size of the planets, apparent size of the planets, throughout their orbit and the orbit of the Earth. And this is why at certain times the planets are better to observe than at others. It's not all just about how high they are in the sky, it's also the proximity of the planet to Earth. So here we've got a lovely composite image of Venus. I'm sorry my face is in the way. From Sean Walker, who is one of the editors at Sky and Telescope. I emailed him, he was happy for me to use this image. And you can see here we've got Venus, a crescent, very close to the Sun, and these are the actual sizes of the planet throughout its orbit. And here we've got Venus distant to the Sun. And you can see, I've put some numbers of arc seconds here, and these are the extremes it does vary with varying orbits. When Venus is in its full phase, it's pretty small, 10 arc seconds, and when it's in its new phase, it's nearly 6 times larger, potentially at 58 arc seconds. And you can see from these numbers that it gets bigger as it gets closer to the Earth, and then smaller as it moves away. Now, this is very simplistic because the Earth is also orbiting the Sun, but I've kept the Earth still just for the simplicity really here. Now, Chris Dole again from the BAA from Newbury, he's allowed me to use these 2 images, and these are images he's taken with his own 180mm Mac Cassegrain. Not from this year, from 2018 and 2019. And these are the closest he's managed to get to a new phase. You can just see here a very thin crescent and the full phase of Venus. Here you can see a nearly full disk. Now, if we go back one slide, you'll see the difficulty here is when Venus is in its full phase or its new phase, it's in the line of sight of the Sun. So this is something to be cautious about if you ever are observing or imaging Venus. It is always close to the Sun as viewed from Earth. But at these phases, it's especially close. And you can see here, in the new phase, it's 6.27 degrees away from the Sun. So that's very close. And you need to take be really cautious about imaging or observing the planet when it is that close to the Sun. And in fact, one of my last slides is a screenshot of an online journal which is freely available, which you can read an article about observing and imaging planets close to the Sun, which carries significant risks to eyesight and equipment. And here, again, at the other extreme, we've got nearly full phase, 99.3% illuminated, and that was just 7 degrees away from the Sun. So I've made those into appropriate sizes, resized them, just to show again exactly where we are. So full phase here, behind the Sun, and then a very thin crescent near the new phase, very close to the Earth. Now, the orbit of Venus is pretty circular, more so than the orbit of the Earth. And the distance of Venus from the Sun does vary. Distance of Venus from the Sun is pretty static at about 108 million kilometers, which is about 0.7 astronomical units. But the distance from Earth to Venus changes, as we've already seen. So when it's at perigee, it's pretty close, and when it's apogee, it's at its furthest. But also, the position of Venus, as viewed from Earth, from the Sun, varies throughout the cycle. We've already seen that at apogee and perigee, Venus appears to be very close to the Sun as viewed from Earth. But at times, Venus is fully separated, maximally separated from the Sun as viewed from Earth. And that's obviously when it's to the east of the Sun, and we call this the greatest eastern elongation. And what happens, what happens here is in the morning, you can see the Earth spinning here, you'll see the Sun rise, and then the Sun will go into the sky, and then eventually Venus will rise, and that will be in daytime. So you won't see Venus with the unaided eye. But then in the evening, the Sun will set, and then for some time afterwards, as we're observing now, Venus will become illuminated in the twilight sky, and then Venus will subsequently set. And this is when Venus is the evening star. So you won't see Venus throughout the day because it rises after the sun and will be in a fully daylight sky, but then it will set several hours after the sun and you'll see it in the evening. So that's one of the furthest separations from the sun as viewed from Earth. The other one is the other side of its orbit, and we call this the greatest western elongation. And again, you imagine in the morning now, as the Earth turns towards the sun, the first thing to rise will be Venus. So Venus will become apparent in the morning twilight sky, and then sometime after Venus has appeared in the eastern sky, in the morning twilight, the sun will eventually appear. And this is when Venus is the morning star. And again, in the evening, Venus would set first, and then the sun. And that's not the phase we're in at the moment. We're in the greatest eastern elongation, so we can see Venus in the evening sky. Now, ancient peoples thought the morning and evening star were two different objects. But about 1 to 200 BCE, the Greeks realized it was actually the same entity. Now, the last part of my talk is just to show you some interesting graphs from this fabulous website called inthesky.org. And this is run by Dominic Ford, who works in Cambridge. And you can plot various things on this website. And what this is showing is the angular separation of Venus from the sun. So we can, and the orange line is today's date. And you can see over the course of an orbit of Venus around the sun, the distance as viewed from Earth of the sun and from Venus from the sun increases to a maximum of just over 45 degrees over a reasonably shallow curve, but then rapidly Venus gets much closer to the sun as viewed from Earth. So this is greatest separation, greatest eastern elongation, and then Venus gets close to the sun again, and this is at perigee, so close to the Earth, new phase, and then it starts rapidly to distance itself again from the sun. This is the greatest western elongation, and then slowly orbits back to apogee, furthest from the Earth here, where again it is close to the sun. So you could do lots of things with these graphs. There's another one here of angular size. Again, angular size is greatest at perigee, and then it drifts down to apogee again. And there's one more, which is the phase illumination. So fully illuminated apogee, and drifts down to not illuminated perigee, and then back up again. And then the last slide is just that article I mentioned about observations of planets and stars near the sun in the Journal for Occultation Astronomy. You just search for that on Google and you can find that edition from 2014. And that is my talk on Venus and its place in the solar system. Now we've got Gareth, who's going to talk about observing and imaging Venus. Thank you.
Hello and welcome to my section of this month's meeting. My name's Gareth and I've been asked to talk about observing and imaging the planet Venus. Now, April is going to be the perfect time to observe and image the planet Venus because at the moment it's lovely and high in our night sky. In fact, if you go outside or if you look out of a west-facing window, around about 7 o'clock or just after sunset, you're going to see a very bright light up there in the sky. And if you haven't noticed this already, then please take the opportunity to go out there and have a look at that, because it's really exciting to think that you're seeing a planet for yourself with your own eyes. Now, what I'm going to do first is I'm going to talk about observing the planet. It might sound counterintuitive, but actually probably the best way to observe Venus at the moment is with the naked eye. The reason for that is, with the naked eyes you get a lovely wide field of view, much wider than you would get with a pair of binoculars or a telescope. Now, what's the advantage of that? The advantage being that when you go outside to look at the planet, it's going to be up there in the sky with lots of other things. So, for example, the other day it was in the middle of the Pleiades star cluster. A few days before that, it was there with the crescent moon. So it makes some beautiful shapes and patterns in the night sky. The other thing is you can watch it as it slowly drifts down the night sky, and it sets quite a long time, probably 2 or 3 hours after the sun. So it slowly drifts down into the west and then below the horizon 2 to 3 hours after sunrise. Now, the reason it takes so long to go down below the horizon at the moment is that it's just gone through what's called greatest eastern elongation. So if this is the sun and I'm the Earth and this is the planet Venus, that's where Venus is at the moment in relation to our point of view. Very soon it's going to go in front of the sun and then it's going to reappear in the morning sky. Now, the reason that we're doing this month's meeting about Venus is it's really about making the most of the opportunity that we've got, because it'll be about 18 months or so again before it's up there in the night sky, when it's much more convenient and easy to observe and image the planet. In the morning, it's much more of an effort to get up and get all of the equipment out and get there before the sun itself rises, and that can obscure the image of the planet. So it really is a golden opportunity at the moment to get out there and get observing the planet, or even just from a west-facing window would be just as good. Now, if you have them, one of the things that you might also want to try is a pair of binoculars. These are mine. These are Olympus 10 by 50s, and they're nice and light, so it's quite easy to get them quite steady when you're observing the planet. The reason you want your binoculars quite steady when you're observing the planet is the fact that if you can hold them quite steady, you might notice that the planet itself at the moment isn't a perfectly circular disk. It is in fact more of a half moon shape. And the explanation for this is quite interesting. Again, if that's the sun and I'm the Earth and the planet is there, the sun is currently only lighting up that half of the planet. So it's showing phases just like the moon itself does. Galileo, I think, was the first person to notice this, and that was actually one of the clinching pieces of evidence he needed to prove that it was actually the sun at the centre of the solar system rather than the Earth, because if Venus was going through phases, that must mean that it's going around the sun in front of us rather than vice versa. Now, if you have one, what you might want to try is a telescope. And here's mine that I've got out to show you. This is a 5-inch Maksutov Cassegrain, and this is the kind of telescope really designed for lunar and planetary observing. The reason for that is this design of telescope uses lenses and mirrors, and the light from whatever you're looking at comes down the telescope, through the front lens, hits the primary mirror, back up to a silvered spot, and then back down the tube again, and out through the eyepiece. And that particular design of telescope means it's really portable and small, because even though the telescope is only that long, it's actually technically 3 times as long because the light's going up and down the tube 3 times. But also it means you can really pile on the magnification. So this is a focal length telescope of 1500, and I put in my 25mm eyepiece. I'm going to get a magnification of about times 60. If I put my Barlow lens, which is a 3 times Barlow lens, which increases the magnification of the eyepiece by times 3, I could get it right up to about 180. The reason I keep it lower, about times 60 magnification, is what you're not doing then is magnifying a lot of the wobble of the Earth's atmosphere, because the planet gets high, but not that high. So we're still seeing it through quite a lot of the Earth's atmosphere. So we get quite a lot of wobble, therefore. If you keep the magnification a bit lower, then you get a much crisper and a much more enjoyable image. What are you going to see through a telescope? Well, you're going to see that phase that I was talking about, those phases that the planet goes through really easily. And if you use a filter, so for example, you might want to use a blue filter or a yellow filter, you can cut out some of the wavelengths of light that you don't want, and that can also help with the shimmering and the twinkling and the wobbling around of the image. Some people who have really large telescopes and use specialist filters like infrared filters and things like that, they claim that they can see the clouds and cloud formations in the surface of the planet. But with a telescope this small, all you're going to really see is a very bright light and whatever phase it's going through. The reason it's so bright is because the planet itself is covered in very, very thick clouds, and the sun's light reflects off them and it makes the planet extremely bright. So it's a lovely thing to look at for a telescope if you get the opportunity. But do try and get some magnification on there without going too over the top, would be my best piece of advice. If you're not just content with observing the planet through a telescope or binoculars with naked eye, you might want to try imaging the planet. Now, you might assume that just putting a stills camera up to the telescope or your mobile phone will be a good way of imaging the planet. But it's often not the case because of that thing I mentioned earlier, the Earth's seeing and the Earth's atmosphere being so wobbly. Counterintuitively, a video camera is actually the best way to take a photo of a planet. And here's the one that I use. This is a very basic model. This is the ZWO ASI 120MC, which is a colour planetary imaging camera. The really serious and dedicated planetary imagers, they actually use monochrome cameras and filter wheel sets to image the planets. And the reason for that being is that you get a much crisper and sharper image and high definition image doing it that way. But because I'm not enormously into planetary imaging and often push for time, for me the planetary colour camera does the job just as well. It's basically just a webcam. The camera sensor's in there, and you've got the nose cone there, and it fits in exactly the same place as the eyepiece does. All you then need to do is open your planetary capture software. I use a thing called SharpCap, which is free on the internet. Search the sky, get the planet square in the chip of the sensor, and get it all in focus, and you're ready to go. Now, anyone that's tried that will probably be able to tell you just how hard that actually is. I've made it sound really, really easy. You know, a planet is a very, very tiny thing. Even though they're enormous, they're so many millions of miles away that actually getting the tiny planet on the chip of the sensor can be very, very frustrating. So it's not quite as straightforward as easy as I might have made it sound there. Let's just imagine though, for sake of argument, we've got the planet focused and sharp in the camera, and it's up on the screen. We then take maybe 500 or 1,000, some people do 2,000 images through the camera. And what you end up with is a video clip. This process is called lucky imaging, because if you're taking that many hundreds or thousands of images, some of them are bound to be sharp as the image is wobbling as it comes through the Earth's atmosphere. So it's basically just a process of luck. Once we've got our video clip, we can load it into another piece of lovely software called Registax. Now, people are so into their astro imaging and they're so keen to share their ideas and their innovations with the astronomy community that a lot of this software is free. Registax is free, and it's absolutely brilliant. You put your video into the software, it rejects the worst images, it keeps the best ones, and it stacks them one on top of the other. You end up with a lovely sharp image, and stacking those images gets rid of a lot of the camera noise. The other amazing thing about Registax is it comes with a function called wavelets, which allows you to adjust the brightness and the contrast. It allows you to play around with the sharpness settings, and it allows you to align the RGB, so if the colour's not quite looking right, you can use the different settings on the wavelets. Export that as a file. I always use TIFF files because they tend to be the best quality imaging files. Then load that into your favourite imaging software. I always use Photoshop just to tidy it up a bit, maybe a bit more sharpening, maybe adjusting the colours, the brightness, the contrast, the levels, all that sort of thing. And then you can save that and share it on social media or email it to your friends and family. And it's a nice way of recording the planet, because as I say, it only gets up there nice and high in the evening sky once every 18 months or so. So it's a nice way of recording your observations of the planet. And if you did it over a series of weeks, you'd actually get to see it changing in phases. As it comes towards the Earth, it will get bigger, but become more of a slender crescent, because again, there's the sun, there I'm the Earth, there's the planet. As it's coming towards us, less of the surface of the planet is being illuminated by the sun, just like with the moon. And you might think that would mean it would get dimmer. That's not actually the case, because it's getting closer. So it stays roughly about the same magnitude. But as I said, it will then go in front of the sun and reappear in the morning sky when it's much less convenient to observe or image it. One last thing I was going to mention is something of a legend about the planet Venus, and that's something called the ashen light. Now, some people claim that when they look at the planet through a telescope, you can actually see the side of the planet which isn't being illuminated by the sun. There's a very faint grey image in the telescope. A lot of people think that this is a myth, but some people, including Patrick Moore himself, have claimed that that's something that he's actually observed. Patrick Moore had some huge telescopes at his house. He had like 16 or 18-inch reflectors. So there's a good chance that he might have seen it. So a challenge for you might be to go out there with your telescope and see if you can see or even image the ashen light for yourself and put that myth to bed once and for all. As I said earlier, now in April is the perfect time to go out and image and observe the planet. So please take the opportunity. And thank you very much for listening. I hope that this has been useful to some people, and I appreciate your time. Thank you.
Good evening, everyone. My talk tonight is on transits and occultations of Venus. So you've already heard how to observe Venus through a telescope and a bit about its orbit from Gareth and James. My talk combines both of these and looks at what happens when the planet, when viewed from the Earth, aligns with different celestial objects, which we term either a transit or an occultation event. Unfortunately, the chance to observe a transit of Venus for us is now over. Such is the rarity of these alignments, as we will discuss later. So first we'll start with a definition of what a transit is. A transit is when a celestial object, such as a planet, passes in front of a larger body, such as the Sun. When this alignment bisects the Earth's path, we see the larger body partially obscured, as you can see in this video of the planet Venus encroaching onto the disk of the Sun. It's different to a total solar eclipse of the Sun, where the Moon, which has the same angular size as the Sun when viewed from the Earth, totally obscures the sphere of the Sun. The transit of Venus appears as a small black dot across the disk of the Sun. It is visible with a suitable solar filter with the naked eye, unlike the transit of Mercury, which requires some form of magnification or projection to observe. So these images from the 2012 transit of Venus taken by the NASA Solar Dynamics Observatory show some spectacular image of the transit from space. The 2014 and the 2012 sequence of transits was the first time a transit had ever been imaged at these wavelengths, and also the first time they'd been imaged from space. The video and images displayed here are constructed from several different wavelengths of extreme ultraviolet light and a portion of the visible spectrum. Ultraviolet light has the advantage of showing surface detail on the Sun, such as prominences, solar flares, as well as the solar corona. These views extend the viewing of the transit outside the photosphere of the Sun, which is what we're limited to. And that image there shows the Venus against the corona, or the Sun's atmosphere. So Venus falls into a class of planets able to transit across the Sun's disk as seen from the Earth perspective. The only other planet that can do this is the planet Mercury. These are termed inferior planets because they lie closer towards the Sun than the Earth. The other planets lie outside the Earth's orbit and are hence called superior planets, and they never obscure our view of the Sun because they always pass behind it. So we'll talk a bit about the frequency of transits. So why don't transits occur more often. You'd expect perhaps that each time the Earth aligns with Venus at an inferior conjunction, you might expect to get a transit of Venus across the disk of the Sun, but we don't see that. It takes Venus 225 Earth days to orbit around the Sun, so you'd expect Venus overtaking the Earth quite frequently would result in a transit. To try and show this, you can see the inferior conjunction of Venus that is due on the 4th of June this year. And you can see there that Venus actually passes above the disk of the Sun, and we don't actually see a transit. So why is this? So to try and explain, I've created a diagram that may or may not make this a bit more clearer. At the top, you've got the orbit of both Earth and Venus around the Sun. And at the bottom, you can see a view from the ecliptic. And this starts to explain why we don't see a transit very frequently. So in this diagram, you can see that the orbit of Venus is actually inclined to that of the Earth by 3.4 degrees. So transits can only happen when this alignment of the two planets and their orbital planes intersect. And these points are called nodes, which you can see by the grey line. And there's two nodes that occur in the orbit, one in December, which is the ascending node, and one in June, which is the descending node. So if I play the animation through, you can see the orbits of Venus intersect in inferior conjunction there, but you don't see a transit because they're not on the same orbital plane. There they are, so you can see a transit. And once again, a conjunction, the orbits mean that the inclination results in no transit. So it's a little more complicated than that in terms of the cycle and the alignment that is required to repeat this transit. So the cycle is actually, well, there's two. There's a 121.5-year cycle, and that is from the December node. And there's also a 105.5-year cycle from the June node. So Venus transits occur also in pairs separated by 8 years. This is partly because of the orbital periods of Venus and the Earth are in an 8-year resonance. So Venus completes almost 13 orbits of the Sun in the same time it takes the Earth to complete 8 orbits. And that's why we see these pairs of transits of Venus separated by 8 years within the 121.5-year cycle and the 105.5-year cycle. So these are the transits of Venus from 1601 to 2200. And you can see that since the invention of the telescope in the 1600s, there's actually only been 8 transits that have been visible. So you can see this cycle within this table. So we can split them up into pairs separated 8 years apart. Then between these pairs, we can see the 121.5-year cycle appearing. Then you get the 105.5-year cycle appearing. Back to the 121.5-year cycle, repeating again on the 105.5-year cycle. So that allows us to predict when the next transits will occur. And it's not until the year 2117 that we next see the transit of Venus, followed by 8 years later in 2125. And both of those are the December node transits. So here you can see the inferior conjunction that I mentioned coming up in June in 2020, and you can see the alignment isn't quite that on the node where we'd see a transit. So we see the passage of Venus pass above north of the disk of the Sun. So we don't see the transit in 2020, 8 years after the last transit that we saw in 2012. As we said, we're into the next cycle now of 121.5 years. So this diagram also shows that as well, the longer cycle. So you can see here the 2004 transit, which we saw brilliantly from the UK from start to finish, and the one that we just saw ending at sunrise in 2012. And you can see as those conjunctions progress further north, the lines don't intersect the nose correctly in June, so we don't see a transit, and the passage of Venus is north of the disk of the sun. And that continues progressively through until the cycle loops back round, and we see our next transit in December 2117, and that starts the next pair in December 2125. So a little bit about what we observe during a transit. We look at what's called contact points, and these are what the timings are used and recorded, and which have quite useful astronomical significance because they have been used historically to estimate the astronomical unit, which is the distance from the Earth to the Sun. So the timings are the observations really that are made during a transit, and they occur at what we call contact points. And there are 4 contact points during a transit that you can define and time. So contact 1 is as the planet Venus enters the disk of the Sun. So when it first touches the disk of the Sun, that is classed as contact 1. When the entirety of the disk of Venus is on the Sun's disk, that is determined contact 2. Contact 3 is towards the end of the transit, when the disk first touches the edge of the limb as it exits the solar disk. And contact 4 is the final contact of the transit, and that is when the transit ceases. So they're the important observations that you would take. The reality of actually observing those is quite difficult. There's various phenomena called the black dot effect, which makes the actual recording the timing of that contact really quite difficult. Okay, transits are themselves quite spectacular, but perhaps more for their rarity than their visual appearance. Although it is the only time that you can actually see the actual full disk of the planet Venus, but it is actually a silhouette of the planet on the Sun's disk. But historically, these events have been really important. Transits of Venus have had great historical significance to science, having been used to determine and calculate for the first estimates of the astronomical unit, that's the distance between the Earth and the Sun, using a technique called the solar parallax. This was achieved by observing transits of Venus from different points on the Earth's surface and precisely timing when Venus started transiting across the disk of the Sun at the various contact points. There was a particular challenge in the 1700s when this was first tried, mainly because the clocks weren't particularly advanced, so the actual timing of this event was very difficult. Telescopes weren't so advanced, so the optics perhaps weren't as good. But mainly the travelling, basically you want to get as far away as possible from the other observation to reduce the errors in the solar parallax calculations. So actually a lot of voyages to different parts of the country were all fraught with all sorts of problems, and some of the actual transits weren't even observed from these locations. So observations from different latitudes on the Earth's surface of the transit, you actually get a different timing due to this parallax effect from 2 different locations. But it allows us to use trigonometry to calculate how far the Sun is from the Earth, once we know the timing of these different contacts and also the distance the 2 observers are apart. So we'll look a bit more about the history of the prediction of transits and the first observations using telescopes in the mid-1600s. So this is a portrait of Johannes Kepler, and he was the first to accurately predict the transit of Mercury in November 1631, which was also the very first planetary transit ever to be observed, and only 3 people are thought to have observed it, including Pierre Gassendi, who observed it from Paris. However, unfavourable conditions across Europe, as well as possibly the size of Mercury on the disk of the Sun being much smaller than had been predicted, probably accounted for the lack of any other observations of the transit of Mercury. This was quickly followed a month later by a transit of Venus on the 6th of December 1631. However, as far as we know, there were actually no observations of this transit, as it was not visible widely across Europe. And this is just an animation showing that transit in 1631 as Venus goes across the disk of the Sun. As I said, this wasn't visible from Europe, and it was largely would have been visible from the Southern Hemisphere. There was also quite a small transit, almost what we call a Gray's transit, where the actual disk doesn't enter the full of the disk of Venus, doesn't enter the full disk of the Sun. So Kepler predicted these transits, but he would not actually live to see either of them. He died just a year before the two events. So we said earlier the transits of Venus comes in pairs, and it wasn't long before the next transit was due. And that occurred 8 years later in 1639, but it had not actually been predicted by Kepler. He made an error in his prediction. He knew about the 120-year cycle, but wasn't aware of the 8-year separation between transits. But a young Jeremiah Horrocks, who had been working on the motion of Venus, discovered the planet's next crossing was due the following month, in November 1639. He was the first to ever observe a transit of Venus from Carr House in Much Hall in Cheshire. It was actually visible during the whole of the day, but Clowes meant he could only observe it for the last half an hour of the transit before the sunset. And this is an animation of what that transit in 1639 would look like. And you can see there, as Venus traversed the disk of the Sun, it's only about halfway across the disk before the Sun would have set. So his friend William Crabtree also knew about this. He was located not far away in Manchester, and they were the only two people who were thought to have observed the transit. Interestingly, it would be some 80 years before anyone else would join them. That's probably quite a historical parallel to perhaps the 12 men that have stepped on the moon, a feat that hasn't been accomplished in over 50 years now. And this is a diagram that Horrocks took of the transit of Venus in 1639, and you can see just how small actual Venus is on the disk of the Sun. So the next sequence of transits occurred in 1761 and 1769, and they're eagerly awaited by the astronomical community as an opportunity to calculate the astronomical unit. So Horrocks wasn't able to do that. He just observed the transit from his home. There wasn't the facility and the organisation to send people around the globe at that point in time, but the 1769 transit was when this really became possible. So it just shows one important event. This image here of the King's Observatory at Richmond in London was built by King George III specifically to observe the transit in Venus in 1769. And I was lucky enough to go round it later last year, and that's me on top of the roof of the observatory, and you can see the observatory in the background. And this is actually a view inside the observatory looking upwards. That's not the original telescope. The original solar heliograph has actually been removed, but it's quite an interesting place to go with immense historical significance to that location. And they were able to actually observe fully that transit in June 1769. And this is a quick animation showing what that transit would have looked like from Nottingham. This Venus transit across the disk of the Sun. Interestingly, this event also incorporated a total solar eclipse the following day. That it was actually visible as a partial eclipse here in the UK, but up in northern Greenland, as you can see here, the Venus transiting across the disk of the Sun. Early the next day, you can see the moon passing straight across the disk of the Sun and producing a total solar eclipse. So it's quite a unique set of astronomical circumstances that went into producing those two events, just separated less than a day apart. So transits of really great historical significance. They were used to determine the astronomical unit, and a lot of time and expense was put into sending observers all around around the globe to observe them. So now move on to different types of transits and also start to incorporate occultations. So we talked about a transit of Venus across the disk of the Sun, but we can also get a transit of Venus across some of the bigger planets like Jupiter and Saturn. So talking about mutual planetary events, just to explain what those are. So they can occur as either a transit or an occultation. So explain what a transit is. An occultation happens when one object passes behind another, usually a much larger object from our perspective obscures another object, and that's what we call an occultation event. So here I've listed some mutual planetary events, either occultations or transit as a planet Venus, and you can see just how rare they actually are. So these are all of the occultations and transits involving Venus from 1600 to 2022. And you can see there isn't actually 2200. There isn't actually many. Indeed, only 11 have occurred since the invention of the telescope of any planetary transit or occultation. Interestingly, only one person has ever even observed one of these transit or occultation events. This was a chap called John Davies, and he observed the Venus occultation of Mercury in 1737. It was really difficult to observe. It was just 22 degrees elongation from the Sun. And this is just an animation of that event showing what Davies would have observed. And you see Mercury beginning its transit behind the planet Venus. And now you can see it just approaching the disk of Venus. And it's completely occulted by Venus. So only one person was believed to have ever observed that. It was John Davies, and he was also credited with discovering the Crab Nebula. So the next such event, as that occurs in November 2065, and that is Venus transiting across the disk of Jupiter. This is just a quick animation of that event. Again, a difficult one to observe, just 8 degrees elongation from the Sun. And you also note that this occurs during the day, making it even more difficult to view. And it's only just a short grazing transit as well. And this is a closer image to show what a small transit event it will be. And after that, the next most favourable planetary transit to observe will be in 2123, when Venus transits Jupiter. Again, this will be very close to the Sun, slightly further than in this one in 2065. It will be 16 degrees from the Sun, but equally difficult to view. So another type of occultation is what we call stellar occultation, and these are the ones that involve Venus. And you can see that these also are very rare events to occur indeed. So the last one to occur was in 1959, which was Regulus occulted by Venus. And the next one won't be until 2044, which is the same Regulus occulting Venus. So only 6 such events have occurred in the last 2 millennia and 14 due in the next 2 millennia coming up. So it really shows how rare these events actually are. And this is a list of any magnitude 2 or lower stars that are occulted by a planet. This is just another animation showing that occultation event in 2044 of Venus going over Regulus. It should be noted that these events are actually useful astronomically, as the rings around Uranus were first discovered when the planet occulted a star in 1977. So they do have astronomical value, as well as just being an interesting event to observe. So I've talked quite a lot about transit and occultations. They're actually very rare events, and none of those we're going to see anytime soon, and many not in our lifetime. So I decided I'll end with one event that we can actually observe, and hopefully that's coming up in June this year. And that is actually a lunar occultation of Venus, which will be visible from the UK, probably with quite extreme care. It starts about 8 in the morning. The moon is just 4% illuminated and will be in the full glare of the sun, so a telescope well pointed will be needed to observe that. And the moon is only 20 degrees from the sun. Venus itself will just be 8% illuminated at magnitude -4. So that's the event we can look out for, and this is just a quick animation showing what will occur about 8 o'clock on the 19th of June. We did actually have a chat with Pete Lawrence, and he says that this event should definitely be visible if you've got a good telescope, so it's one well worth keeping an eye out for. So that concludes my talk this evening on the transit and occultations of Venus. There are numerous books on the subject if you want to explore it in more detail, but thanks very much for listening.
Hello everyone, and welcome to a quick presentation on how we've managed to try and explore Venus using space probes and how hard it can be. So let's get into it. The first thing is to look at, this is a nice animation that shows the relative positions of the planets Venus and Earth, and you can see that every so often they get quite close to each other and then they spend quite a long time apart. So every 584 days the conditions are just right for a mission to be launched, and you can see it gives a rather nice pattern from this. So every sort of couple of years there is a window where it's ripe for a mission to Venus, and we've had quite a few of these with or without success. So let's see who's done what over time. So the very first people to try and get to Venus were the Russians with this spacecraft, one of their Sputnik series. This was called, I can't pronounce that, but it means heavy satellite test. It was meant to go to Venus and it got into orbit, but it failed to leave orbit. So they, when they released the details about it, they said it was just a heavy satellite test. It wasn't really an attempt to go anywhere else, but really its original intention was to go to Venus and to have a look at it. But the publicity machine meant that because it was a failure, they didn't publicize that. And this is quite common throughout the Russian attempts. So after that, they did manage to get probes launched to Venus. This and the ones that did go to Venus were all called Venera, or certainly in the early days. So Venera 1 was the very first one in February 1961. This one flew past Venus, but unfortunately they lost radio contact just before the flyby commenced. So they didn't really get very much data, but it was the first probe to get close to Venus within 100,000 kilometers, which is pretty close, astronomically speaking at least. The next one was Mariner 2, August 1962. This got within 34,000 kilometers in December 14th. This was Mariner 2 because Mariner 1 had failed to launch. This was one of the catalogue of failures of the early space probes that happened, particularly with Venus. So these are quite a number of cases of things that have failed. So Mariner 1, we say, failed to get into orbit. So this would have perhaps come to Venus, but didn't manage it. Then there's a whole host of these Russian ones. This 2MV1 number 1, which the upper stage failed, and number 2, and so on. These would all have been Venera probes if they'd managed to get towards Venus, but they all failed either getting to orbit or failing to leave orbit. So they were all just classified as either these MV1s or Cosmos probes or Zond or one of those things, but they weren't given an official Venera description. The second one to get anywhere near was Venera 2, November 1965. This got within 23,000 kilometers, and they did attempt to record data. So when it got this close, the spacecraft switched to, instead of sending data and recording to Earth, it switched to recording data from Venus and saving it up. But unfortunately, they didn't manage to re-establish contact and get all that data back. So we never managed to get any of the data that it had recorded, and that was not a huge success from that one. Venera 3, this probably managed to impact into Venus, but we're not quite sure. The Russians lost contact with it before it got to Venus, so we're not quite sure exactly what happened, but the suspicion is it probably impacted into Venus on March the 1st, 1966. But we don't have any definite proof of that. Next one was a more ambitious Venera 4. This was a probe that was designed to land onto Venus and indeed made atmospheric entry into Venus's atmosphere in October 18, 1967. It was quite well engineered, had a parachute capable of withstanding heats of 450 degrees centigrade. It was stressed to withstand 450 G loads, and its heat shield was supposed to be able to cope with temperatures up to 11,000 degrees centigrade. But it failed on its way down. So it recorded a certain amount of data, but at about 55 kilometers above the surface, it failed at a temperature of 262 degrees centigrade and 22 atmospheres. And this was probably just due to lacking the power, because the atmosphere was somewhat thicker than they'd expected. So the parachute they'd packed for it went quite slowly through the atmosphere, so it was a very slow descent, and just ran out of battery as it descended through there. Mariner 5 was an American mission that went off in 1967, went past at reasonably close, and because it was occulted by Venus, managed to record some signals passing through the atmosphere, which helped verify some of the Venera data. Then Venera 5 and 6, these were yet again attempts to land on the surface. They had atmospheric entry, very, very similar design to Venera 4, but much strengthened. And also the parachute was made a lot smaller so that it fell faster, hoping to eke out the battery life until it got lower. It succumbed at about 320 degrees centigrade and 26 atmospheres. So a little better, but not quite as close. Venera 7 in August 1977. This was designed to cope much better, but its parachute failed eventually. It got twisted up on its way down and eventually shredded and failed altogether. And we think it probably hit the surface at about 47 miles per hour. And they thought they'd lost it completely, but there was, on subsequent examination, a very weak signal coming from it for 23 minutes. So it had probably crashed into the surface and fallen over on its side, and had measured a temperature of 475 degrees centigrade. So a very, very hot place with a very thick atmosphere. The next go, Venera 8. This one was more successful. It landed, and the probe actually landed and lasted for 50 minutes on the surface, confirmed the 470 degree temperature, and it also had a light meter amongst very many other instruments, which confirmed that it was enough light there for photography to take place. So a camera placed on the probe would have been successful. The light levels were much like a very overcast day on Earth, basically. Mariner 10, another close flyby, February 1974, 5,000 kilometers, but it's principally aimed to go to Mercury. So it took some readings as it went past, but then went on to Mercury. Then we're back with the Russians, Venera 9 and 10. These were, again, atmospheric entries, and this time they managed to descend to the surface, land successfully yet again, and this time take photographs. So here we have a black and white photograph of the surface of Venus. See, it's quite rocky. Can't see very much more detail. Then we have some American missions, Pioneer 1 and 2, or Pioneer Venus, March and August 1978. These went into orbit for quite considerable time, as you can see there, from December to October 1992. Surface mapping and atmospheric probes to work out what the conditions were in the atmosphere and map Venus by radar. Then we're back to the Venera with 11 and 12. These were two more attempts to get to the surface. They succeeded in getting to the surface, but both had colour cameras that failed. They failed to lose their lens cap basically as they came down, and so neither managed to take any images of the surface. Venera 13 and 14, though, were much more successful in 1981, much the same as the previous ones. They also had microphones on board so they could listen to the surface, and managed to land and take the first colour pictures of the surface, which we can see here. The original as seen on the surface, and with the atmospheric effects removed, you can see there the surface of Venus. Next one was Venera 15 and 16 in 1983. These were just orbiters that attempted to map the surface of Venus and did so reasonably successfully. Then they switched and they called these next two probes Vega because they were also going on to extended mission. These quite ambitious. They had a flyby of Venus and dropped off a balloon and lander on the way. So these went on to study Venus, but the main part of the probe then went on to Comet Halley because they found that the orbits were conducive to actually making that trip. The lander wasn't hugely successful because it encountered some severe turbulence on its way down through the atmosphere, which tripped the instruments and they thought they'd landed or something like that. So they activated actually 20 kilometers up, so prematurely. So by the time they got to the surface, there wasn't very much battery left to record any signal. The balloons were more successful. They orbited around the planet at about 50 kilometers in their high wind speeds there and transmitted data until they sort of blown out of range of the ability to transmit data back. Then we're on to American NASA probe Magellan, May 1989, lasted until 1994. This was launched from the space shuttle and used Venus for the atmosphere for aerobraking, so quite a novel approach. And this was primarily a mapping mission. So this was a 4-year mapping mission of Venus, which was probably got us some of our best maps of Venus. Venus Express was an ESA mission, 2006 to 2014. This went into polar orbit and was a long-term study of the atmosphere and also radar mapping of the surface. And the final mission was Aksuki, a Japanese JAXA mission, May 2010. It was supposed to go into orbit around Venus in 2010, but unfortunately there was a malfunction with the main thruster, and it only fired for a short period compared to what it should have done. And it went into then a solar orbit that 5 years later came back to Venus, and at that point they managed to lighten the load of the spaceship enough that they used alternative thrusters to slow it down and get into orbit of Venus at that point. And they took some interesting pictures, including this UV picture of Venus from close by. So that was really the final one. There's been a few other missions that have gone past Venus, but usually on the way to other planets. So Bepi Colombo, for instance, is going past Venus, and Messenger also went past Venus, both on the way to Mercury. And there's other probes that have got on to Jupiter that have used Venus as slingshots. So with that, that's my bit done, and just basically says that Venus is a little bit harder than you think to map and to visit.
Right. I think we're about ready for questions. Julian, are you there? Richard?
I am.
Good. So, thank you all for the talks. Olwyn's asked a question. Richard, can I have the screen?
Yep, should have that now.
Let me share my screen. So, Olwyn's question was, why is the eastern elongation on the left and the western elongation on the right? So here's a view of the Earth looking towards the sun. And obviously from the northern hemisphere, the sun is in the south. As you look out of your garden, the sun will be southerly. Now, to your left will be east as you look south, and to your right will be west. So here we've got when Venus is at its greatest eastern elongation, it will be to the left of the sun, which is on the eastern side, and when it's on its greatest western elongation, it'll be on the right of the sun, on the west side. And what I've done also here is loaded up stellarium, and this is the date for the 24th. It was actually supposed to be 24th of March. Let me go down a month. There we are, 24th of March this year. So this is when the sun was at greatest eastern elongation. And this is at 1 o'clock just after lunch. And you can see the sun in the southern part of the sky. Obviously it's very bright because it's midday. So what I'm going to do is turn off the sunlight, and then you can see what stars and planets would be visible if the sun wasn't so bright at that same time. And you can see here's the sun, and then to the east of the sun is Venus. So that is at the day of greatest eastern elongation. And if we increase the time, if we go forward, 2 o'clock, 3 o'clock, 4 o'clock, 5 o'clock, 6 o'clock, so the sun is now just below the horizon, and if we turn the reality back on, you can then just start seeing Venus in the twilight sky, and it's setting behind the sun. Although it's now in the west, it's on the eastern side of the sun. So hopefully that answers that question. I'll pass the screen back to Richard. Are there any other questions? Julian, can you see any questions?
I think there's one there for Richard probably about what was the date in June this year for the lunar Venus occultation?
Yeah, that was the 19th of June, and it'll be visible from about 8 o'clock in the morning. That one.
He didn't remember that. I saw him looking at a bit of paper. Do you want me to get that up on Stellarium, Richard?
You can do, yeah. Well, I can do it myself if not.
Okay, you do it. I've still got the screen though, I think.
Okay, give me a second. Okay, can you just give the taste back?
You have it.
Okay, thank you. Okay, so you should be able to see that shortly. There you go. So that's the occultation of Venus. I'll just play that through so you can see that in time. So it's just after 8 o'clock in the morning. Going to be quite difficult to see because it's in broad daylight, and if you're going to view that with a telescope, make sure you've got really good pointing accuracy, and it doesn't stray towards the sun because the sun's not far away at all in the sky. But we have been advised it is possible to see it, so perhaps give it a crack if you want to.
There's a comment there about wondered why the transits of Venus had so much historic importance. Yes, I can't remember the intricacies of why they wanted to do that. Julian, can you remember why Horrocks was so keen on?
Well, as Richard said, it was really just to measure the astronomical unit, because at the time they didn't really have a good distance to the sun calculated. But I forget who did the original calculations, but someone found that because looking from different parts of the Earth, you see it cross the sun at different levels, and also translates into a different time. So that's why the timing is important. You can then do the trigonometry and work out using triangles and stuff exactly what distances there are involved.
I think certainly a lot of the measurements taken in the 1730s were quite poor, and didn't even release some of the calculations. They were that unsure as to the accuracy. The later one, I think they were able to get people much further spread around the globe, so that made a massive difference to the actual calculations and the accuracy of them.
Yeah, the wider you can get the sort of baseline between observations, the better, I think.
Yeah, and then I think by the 1800s, other methods had come in that were more accurate in determining that sort of distance. So the actual need to use a transit became less important later on.
Yeah, you could do it by radar, I think, in the 20th century. There's another one there from Brendan, I noticed. Do you know if any spacecraft have detected any current activity on the surface of the planet, like molten lava areas, or do we think its geoactivity has ceased? That's a really interesting question, actually. I've got a feeling, although I can't actually say definitively, that we have detected geological activity. The odd thing about Venus is it doesn't have, well, maybe it's not odd, but it doesn't have tectonic plate activity. So what seems to happen on Venus is that it's still got a very hot molten core, so the pressure seems to build up, and it sort of gets to a certain point, and they believe the surface of Venus sort of cracks open, and magma flows out and resurfaces the surface of Venus. So the surface of Venus is always relatively new. I think it's something like every 500 million years or something like that. It sort of goes through this resurfacing. So there should be volcanic activity on the surface. There are certainly large volcanoes being detected, but I don't think we've actually seen any volcanic activity, because you can only see through the clouds with radar, and the resolution of radar is not very fine to see details like that. But I think maybe infrared or something like that has shown hotspots.
So, Julian, I've just loaded up the current BAA Mercury and Venus section publication, and Paul Abel's the section director there, and in it he said, as I've remarked in the first edition of Messenger, that's this publication, now is the time to try and image the night side of Venus, particularly when the phase drops below 30%. It is possible that active volcanoes might have been recorded on the night side of Venus, and they'll be discussing the technique for imaging the night side in infrared, and encourage all section members to try and send me their results. So
fabulous.
The BAA are looking for IR hotspots on the night side.
Right. There's another question there about the atmosphere of Venus. I think you mentioned something about the atmosphere of Venus, James, didn't you? Its constituents.
Yes, mostly carbon dioxide, and a bit of nitrogen, and then there's the the complex acid rain.
Yeah. So it's a really, really thick atmosphere. It's like being about a kilometre underwater, or even more in some places. So I think it's 90 atmospheres or something like that. That seems to ring a bell. So that's way beyond sort of skin diver ability. You need serious protection to survive under that sort of atmosphere. Plus, it's 450 degrees centigrade. So this is why the Russian probes didn't last particularly long. Once they got there, they were under enormous pressure and had to keep very active cooling just to keep the electronics from frying. So very, very nasty atmosphere. It's basically a runaway greenhouse effect. So what's happening on Venus is probably what we've got to look forward to. And on that cheery note,
we've stunned everyone into silence.
That was our purpose.
Right, so there aren't any more questions. Thanks everyone for tuning in. Let us know what you think, and as I said earlier, we do need members to contribute short videos on what they're doing, so we can keep this going. Now in May, on the 7th of May, for the Gotham meeting, we've got Jeremy Shears, the past president of the BAA and the variable star section director. He's going to be giving us a talk on variable stars and is it cataclysmic variables, Richard?
I think so, yeah.
So that will be advertised in due course. And that's it. Thanks for listening. If any other questions appear, we'll get them answered and put them in, get Roy to put answers in the journal. All right. Thank you, everyone. Enjoy the rest of your evening.